If we want to talk about logic circuits, first we need to talk about minterms. Important points about minterms include the following. In a minterm, each variable x, y, or z appears once, either as the variable itself or as the inverse. Each minterm corresponds to exactly one entry or row in the truth table. Implications of the 2 points above are that you can build any Boolean function at all by building it from minterms. Truly, any Boolean function can be constructed using minterms, and the construction process is simple. First, get a truth table for the function. Be sure that all possible combinations of variables and inverses are accounted for. For each entry of the truth table for which the function takes a value of 1, determine that corresponding minterm expression, remembering that every variable of its inverse will appear in every minterm, or all the minterms from the second step together. To illustrate the use of minterms to get an electrical implementation of a logic circuit, consider this problem. 3 young graduates have formed a company: Alicia, Ben, and Corey. They have a system to minimize problems. For all minor decisions, they want to use a circuit that will determine when a majority of the 3 of them has voted for a proposal. Essentially, they want a box with 3 inputs that will produce a 1 at the output whenever 2 or more of the inputs are 1. This is the truth table for that problem. After getting the truth table, the next step is to identify the minterms. The minterms are to the right of the corresponding entries in the truth table. There are 4 1 entries in the truth table and 4 corresponding minterms expression. So when you AND all these terms together, you get 1 under the conditions here. These are the 4 conditions that get a 1 in the truth table. And this is the result, or the f, that will be the function that represents the truth table. Each minterm can be generated using a 3-input AND gate, and the first minterm is shown below. You will need 3 more circuits somewhat like this one for the complete solution. Next, consider how these small circuits must interact. The function is 1 whenever the first term is 1, or when the second term is 1, or when the third term is 1, or where the fourth term is 1. To implement that, you'll need the following circuit. Now let's talk about max terms. A max term is a logical expression of n variables consisting only of the disjunction and logical complement operator or denial. Max terms are the dual expression of minterms. Instead of using operators, we use and, or operations proceed similarly. This is an example of a max term and how you can write it as the example on the right. Like minterms, maxterms also provide a way to represent any Boolean function algebraically once its truth table is specified. For example, for the same function as previously, we observe that it is 0 on rows 0, 3, 5, and 6, so the function will be equal to that. And this is how you can write the minterm or the max term for that function. Then we will talk about the karnaugh maps. A karnaugh map, or K-map, is a pictorial method used to minimize Boolean expressions without having to use Boolean algebra, theorems, and equation manipulations. The K-map can be thought of as a special version of a truth table. Unlike a truth table, in which the input values typically follow a binary sequence, the karnaugh map's input values must be ordered such that the values for the adjacent columns vary by only a single bit, for example 0, 0, 0, 1, 1, 1, and 1, 0. This ordering is known as a gray code, and it is the key factor with regard to the way in which karnaugh maps work. The Y column in the truth table shows all the zeros and 1 values associated with the gate's output. Similar maps can be constructed for 3-input and 4-input functions. In the case of a 4-input map, the values associated with the C and D inputs must also be ordered as a gray code, as we can see in this picture. Consider an example: 3-input function represented as a black box with an associated truth table. And here we have the truth table and the graphical representation. Any pair of horizontally or vertically adjacent blocks corresponds to minterms that differ by only a single variable. Such pairs of minterms can be grouped together and the variable that differs can be discarded, leaving a much simplified equation. As we can see in this picture, it shows the process. Grouping can also be formed from 4 adjacent minterms, in which case 2 redundant variables can be discarded. Here are the equations for each grouping. As you can see here in the picture, you get the final function based on the minterms.